Hello guys. My the audio on this video is not all that great. But I'll make sure that I speak as clearly as possible. I wanted to go ahead and make a video for you guys so that we could review some things and you could hear my explanations behind it to prepare you for your test, which is coming up on Wednesday. Okay, so this is looking at Theory of Evolution, Part 3, Mechanisms of Evolution. Another way of thinking about this chapter is basically what are the things that cause populations to change? There's another mini subtitle. Okay, so we've been through some of these already as a class, and I'm going to kind of skim through. The first couple pages here is just like general vocab and making sure that we have that foundation, understanding that there can be several populations within a species, and that it's the populations evolving, not the individual. Okay, and then we continue on to talk about how the lost my train of thought. We talk about how the genes are actually the ones that's controlling those adaptations and that evolution behind it. So this second slide very much is just some general vocab to prepare us for the rest of the stuff that's coming. Once again, this is all review. We went over this as a class, and I really just wanted to hit the main points here. So this slide, super important. Okay, it literally summarizes the entire chapter all in one go. Remember, there are 4 things that can change genetic equilibrium. Another way of saying change genetic equilibrium is that there are 4 things that cause populations to adapt or change. Okay? So those 4 things are mutations, migrations, genetic drift, and natural selection. Okay, are those 4 main things. I would definitely know those for your test on Wednesday. Mutation, migration, genetic drift, natural selection. In class, I think I even had you put a star in it, if I remember right. It's been kind of a long week. Alright, with mutations, remember mutations, it's a random and permanent change in the DNA. A lot of times they are lethal out in the natural world, but there are some times where they are actually beneficial. So we gave the example of 2 green beetles making a brown beetle, and that being a beneficial adaptation if it helps that organism camouflage better. And then we talked about migration. So there are lots of instances in the natural world where we have different individuals moving from one population into another. Okay, and the 2 main parts here, so as they move, okay, if they immigrate with an I in, they go into a new population, they are bringing their genes with them. So all of a sudden, that gene pool gets larger because you have an organism immigrating into it. As opposed to the population that left, okay, that individual when it left its original population or emigrated with an E, exited, emigrated, okay, out of that population, it is now losing those particular set of alleles or set of genes. We see with migrations, this is just a side note, a lot of times, especially if there's a large migration where there's a lot of individuals moving, this can cause a pretty dramatic change in that population. And then we got into genetic drift. So there are 2 little subcategories of genetic drift, and these are basically the genes are changing because of chance events. And this is where we talked about bottleneck and founder's effect. Bottleneck, remember, is when you have something, you have a large population, they're thriving, they're living healthily. What happens is that a lot of times there'll be something bad that happens, and a lot of times it'll be like a catastrophe, natural disaster, habitat destruction, hunting, poaching, all of those would be considered bottleneck effects. So you have a big population, then something bad happens when there's only a few survivors, and those that are left to hopefully repopulate that particular area. Okay. What we see is that the gene frequency is going to be a lot larger. There's a lot of genetic diversity before that catastrophe compared to after. Okay. And our 2 real life examples were the northern elephant seal, where they were hunted, that was the bottleneck, and now there was only a few left to repopulate. They did repopulate, but now they have side effects like poor immune system, and they're generally smaller than they once were. The other bottleneck effect is the cheetah. They actually went through two bottleneck effects, which is one of the reasons why they are a threatened species at this time. But their bottlenecks have included the Ice Age, and then the second bottleneck was the hunting and the habitat destruction caused by humans. And so what happened is that left them with really, really poor immune systems because of that low genetic variation. They are extremely close DNA-wise, okay, which makes this not the strongest species at this time. If there was a disease that came around, these cheetahs would be easily wiped out because they have a poor immune system and because there's not a lot of genetic diversity among them. Cheetah, cheetah, cheetah. And then we got to the second type of genetic drift, which is the founder's effect. The founder's effect is where we have a big population and then a section of that population decides to go to another area. A lot of times when we look at animals and if like a small part of the population migrates to a new island, that could also be an example of founder effect. In humans, an example of founder effect would be the Amish population, because they typically marry and mate within that same community of Amish people. Recessive alleles are very frequent. So we see recessive alleles are actually more common than dominant alleles, which can lead to things like dwarfism and polydactyly. Sorry, I had to go get my cat. This teaching from home thing, not so good. Okay. Alright, the last thing is natural selection. So with natural selection, this is where we have seen over and over again that nature is going to determine what are the best adapted organisms and which ones have the favorable traits. Those that are the strongest and the best adapted will be able to reproduce because they didn't die off unlike others. Okay, now there are three types of natural selection. There's stabilizing selection, so you can see in this graph, which we drew in your notes, that the stabilizing selection favors the average. So this is why instead of your normal bell curve like we expect to see, the extremes are going to die off, leaving the average to prosper. I think we gave the example of like oysters in class, but really, if you're taking a look at it, maybe if we were looking at squirrels instead, okay, where you would have like the white squirrel, like an albino squirrel on one end, okay, and then the black colored squirrels on the other, and they're living in a forested area. Well, the black squirrels aren't going to blend in all that great compared to the brown, and the white squirrels will definitely stick out. So therefore, those two extremes would be picked off, and those brown squirrels would flourish. Okay, you would see a big increase in that number because they can camouflage in. That'd be an excellent example of stabilizing selection. Directional selection is where one extreme is favored. So now let's think about, okay, if we had our squirrels, we had white, brown, and black, right? Or albino, brown, black, maybe is another way to say that. And it was living in a cave situation. Okay, and so what we would see is that if this was the white squirrel over here on the left side, and these were the black colored squirrels over here, the white ones would obviously stand out easily, be picked off by predators. The brown squirrels would be next, but those black squirrels, if it was a dark cave, that is actually a beneficial adaptation at that point, causing the population to shift towards that more extreme, meaning that there would be more black squirrels around than the white or brown varieties. Basically the words of what I just said. And then disruptive selection, okay, this is going to be the opposite of stabilizing selection because instead of hating on the extremes, it's going to favor the extremes. Okay, so in this example, if we're thinking about our squirrels again, let's say our landscape was, there was a lot of, like a wooded area right next to a white sandy beach. Okay, and so what we see is that So lighter colored squirrels would actually blend into, I don't know many squirrels that live on beaches, but this is just me making it up on the fly. Alright, so a lot of those lighter colored squirrels would have the beneficial coloration, so they would not be picked off. The black-colored squirrels could hide in within the dark shrubbery that's also there by the edge of the beach. However, the brown squirrels, because they could not blend in either way, we would find that their predators would be able to pick them off because they couldn't blend in as well. Disruptive selection we don't see a lot, but when we see it, a lot of times it can lead into speciation, meaning that eventually, after all these brown squirrels, all these in-between colorations or varieties die off, a lot of times we would actually end up with two separate species. Speaking of species, it leads right into this. So we know speciation is the formation of new species, and for a species to be a true species, it has to be able to breed with one another, and they have to produce fertile offspring. So things like mules, where you cross a horse and a donkey, is not technically a true species because that mule cannot reproduce. They are sterile. Okay, so it has to have offspring, and that offspring also has to have the ability to have babies. There are three things that we see speciation mostly caused by: geographic isolations, temporal isolations, and behavioral isolations. And we saw this in the speciation video that I put up for you on that first lesson. So what geographic isolation is, and I'm not going to read through all these because I am limited to only 15-minute recording and I'm getting close on time. So geographic isolation means that there's something physically in the way of these populations. So for example, if we have a population of beetles and there's a large flood, that water would actually potentially separate out those two populations, causing over time a chance that there are two different types of species of beetles. Okay, because they are physically separated, they can no longer breed with one another, and over time, those populations could adapt or evolve into two different species. Here's an example where they talk about these antelope ground squirrels that live in the Grand Canyon. One lives on the northern ring, the other one lives on the southern ring of the Grand Canyon. They used to be one species, but because of this large canyon, obviously, and between them there's that physical separation, we now have two different species. So what happens is when these guys mate, they actually can't. They have a different, like their chromosomes are not shaped correctly anymore. So the northern ring antelope squirrel, which is the white-tailed one, and the Harris antelope ground squirrel, which is on the southern ring, can no longer mate and actually produce fertile offspring. Even though they look exactly the same in my opinion. Temporal isolation just deals with mating time. So basically it says that even though the species could maybe mate, okay, like these two frog species, they don't. And the reason they don't is because they have different mating times. Okay, and this could be different mating times during the year, or it could be different mating times even during like times of day. Maybe one species mates in the morning and the other one mates at night. Okay, so it all depends on time. Temporal. Temporal refers to time. And the last one is behavioral isolation. We saw this with the birds of paradise video. So this is basically saying that, yeah, different species of birds have the potential of mating, but they don't because of mating behaviors. So for example, we have a bunch of different bird of paradise species, and with those birds of paradise, even though they could mate, they each have that own specific crazy dance they do, which is only attractive to members of that same species. If it was done to another bird of paradise species, they'd be like, no, that's just weird. Or if a cardinal came along and was like, what is that bird doing? Okay, that's what we're talking about, behavioral isolation. They don't mate because the behaviors are just weird to other species. Alright, and then this one we've actually talked about in our last chapter. Speciation usually occurs pretty gradually, which we refer to as gradualism, so small changes over long periods of time. However, in cases like the Industrial Revolution, or sometimes if we have geographic isolation, we see that punctuated equilibrium can happen, which means that it's not a constant rate. It has to evolve or adapt quickly, or it will die off.